Hello and welcome back. Let's take a look at setting up the simplex method. We've looked at solving linear programming problems using graphical techniques, but now we need a method that's going to work if we have more than two variables and we can't graph the feasible region. So we're going to first begin by looking at a standard maximum problem. A standard maximum problem has an objective function that's being maximized. The constraints are always written with the less than or equal to inequality, and the constants are never going to be negative. So what I mean by the constants on the constraints, for example, one constraint could be, say, x1 plus 3x2 is less than or equal to 5. The 5 on the other side of the inequality, that's the constant that we're talking about. So we're always going to have positive, non-negative constants on the other side of our inequality. The other thing, the variables are going to be restricted to non-negative values, so we'll always have a statement like x1, x2, x3, x4, whatever, greater than or equal to 0. Okay, so we're never going to have to consider negative solutions for our variables. So the way we set up the simplex method is we take our linear inequalities and we rewrite them as linear equations by introducing an extra variable called a slack variable. So take a look at the example that we have down here. Our first linear inequality is 8x1 plus x2 less than or equal to 180. So a solution for this inequality could be 8 times 10 for x1 plus 100 for x2. And that would be less than or equal to 180. But we also could have 8 times 10 x1 plus 0 x2, and that would still be less than or equal to 180. However, that wouldn't work if we changed the less than or equals to symbol into an equals symbol. So what we'll do is we will introduce an extra variable that will become whatever we need for the inequality to become an equality. So if my x1 was 10 and my x2 was 0, then we would have 8 times 10, so 80 plus 0. So my slack variable then would have to be a 100, and then it would become an equality. It would equal 180. So we can rewrite our first inequality as an equation by introducing a slack variable. And so I will use s sub 1 for the slack variable. We can do the same thing for the second constraint. We have x1 plus 4x2. And this time we will introduce a second slack variable, s2. And so now we have two equations instead of inequalities. We don't have to do anything for the non-negative conditions because those are just telling us where the feasible region has to begin. So our constraints are given by just the first two inequalities. The number of constraints will always equal the number of slack variables that you have. So we had two constraint inequalities, so we ended up with two slack variables. The second thing that we need to do is rewrite the objective function, starting with, we need to rewrite the objective function, basically getting z and x1, x2, etc. on the same side, and we need the z to have a coefficient of 1. So essentially what we're going to do is we're going to subtract everything onto the same side as the z. So our objective function will become z equals negative 4x1 minus 6x2. Z minus 4. There we go. We're subtracting everything onto one side. So we have z minus 4x1 minus 6x2, and since we subtracted everything onto one side, this would equal 0. The reason that we've done this is because now we have everything set up so that all the variables are on the left side and all the constants are on the right-hand side. Now that we have this, we can go ahead and set up what's called the simplex tableau. So we're going to we have to label our columns so we know which column represents which variables. You will always start with the variables x1, x2, etc. So we'll start with x1 and x2. Then we introduce the slack variables. So we'll have slack 1 and slack 2. And then we'll have the z column representing the z function. And then on the other side will be our constants. So let's see. Let's go ahead and put in our first constraint, which is now an equation. So I'm just like we did with systems of equations, we have 8x1 plus x2 plus s1 equals 180. So I have 8x1s plus 1x2 plus 1 slack 1. I have no slack 2 and I have no z. And now I'm at the point where I have my constant. So this will be 180. And so we'll use that vertical bar like we did before for augmented matrices. Now we'll do the second constraint. We have 1x1, we have 4x2s, we don't have any slack 1, but we do have a slack 2, and we have no z. And our constant is 110. So we've represented the constraints. We don't have to put anything for the non-negative conditions. And then we'll use a horizontal line to indicate that the bottom row is going to be given by the objective function. So keeping the same order, so I have negative 4x1 terms, we have negative 6x2 terms, there's no slack 1 and no slack 2, but there is 1z. And the constant on the other side would be 0. And so this matrix right here, this is what we call our initial tableau, or initial simplex tableau. And this is how we will set up the simplex method. So once we have our linear programming problem inside of a simplex tableau, or an initial tableau, then we can start applying the simplex method. And that's what the next video will focus on. For practice, you should go ahead and take the problems that we did in section 3.4, the linear programming problems that you solved graphically. Go ahead and represent their simplex tableau, because you can do this for any linear programming problem. Whether it has 2 variables or 10 variables, you can set up the simplex tableau. So that's a good thing to do for practice, is to take our previous linear programming problems and go ahead and set up their simplex tableau.